Here are the answers for the section 4-4 homework for day 2 of working on factoring. For number 5, we're asked to factor this polynomial. The first step of factoring is to look for a greatest common factor. Is there anything that divides into this term and into this term? I notice they both have an a, and I notice the first term will divide by x squared, and the other term also has enough x's to divide it by x squared. So the GCF is ax squared. Follow that up with a set of parentheses that is large enough to fit a binomial. Ax squared times 1 makes the first term be ax squared, and ax squared times positive 3x would make this second term be 3ax cubed. Number 9, look for a GCF, but there's not one other than the number 1. Now look for a special pattern. When you see a binomial with a subtraction symbol, the special pattern that you're looking for is called a difference of squares. The first term must be a perfect square. If you were to take the square root of this, it has to turn out to be a monomial that uses whole numbers. 4a squared does have a square root, 2a. You also have to be able to take the square root of the last term. The number 1 is a perfect square because its square root is 1. So after doing those checks to see if this is a perfect square and this is a perfect square, then we will know it's a difference of squares. The factoring pattern has 2 sets of parentheses. To find this spot and this spot, you use the square root of the 4a squared. 2a times 2a is 4a squared. To find this spot and this spot, you use the square root of the 1. Positive 1 times negative 1 makes the negative 1. Number 19, check for a GCF, but there is not one. Now look to see if this fits a special pattern. When you see a trinomial, the special pattern that you're looking for is called a perfect square trinomial. But it's only a perfect square trinomial if certain things are true. The first term must be a perfect square. Does this have a nice square root? Yes, it does. It would be x. The last term must be a perfect square. Is the number 9 a perfect square? Yes, it is, because its square root is 3. Remember, the square root of this was x, and the square root of this was 3. The middle term must be twice the product of x and 3. So is 6x twice x times 3? Yes, it is. Once you decide that this is a perfect square trinomial, then follow the factoring pattern that works for that kind of polynomial, a set of parentheses squared. The square root of x squared is x, the square root of 9 is 3, and this has a plus sign in the middle, so there's a plus sign here. Number 25, look for a GCF, but there's no number that divides into 9, 30, and 25. Now look to see if it's a special pattern. This is a trinomial, so the special pattern that we're checking for is the perfect square trinomial pattern. This has to be a perfect square. Can you take the square root of that? Yes, you can. You would get 3x. This has to be a perfect square. What's the square root of 25? It's 5. The middle term has to be twice the product of 3x and 5. 3x times 5 is 15x. Twice that is 30x. So as soon as you've done all of those checks to know that this is a perfect square trinomial, then follow the pattern for perfect square trinomials. 3x goes here, plus sign in the middle, and the 5 goes there. Page 135 of the written, more factoring. The first step is to look for a greatest common factor. Both terms divide by 3. You write that down and you make a set of parentheses following it. 3 times y squared makes 3y squared, and 3 times negative 16 makes negative 48. Then inspect this factor to see if it's a special pattern. It is a binomial with a minus in the middle. So the special pattern we're checking for is called a difference of squares. Is this a perfect square? Yes, it is, because the square root of y squared is y. Is the number 16 a perfect square? Yes, it is, because its square root is 4. So because these square roots are nice whole numbers, we know it's a difference of squares. The pattern is 2 sets of parentheses. Y times y was the y squared, and positive 4 times negative 4 was the negative 16. Number 4 has a GCF. There's a 9 in both terms, and both terms can divide by s squared. So our GCF is 9s squared. 9s squared times s squared makes 9s to the 4th. 9s squared times minus 1 makes negative 9s squared. Now inspect this. Does it look like one of the patterns to you? Hopefully you notice that this is a difference of squares. So final answer begins with 9s squared, and then the pattern for difference of squares has 2 sets of parentheses. S plus 1, S minus 1. Number 6. There's no greatest common factor other than 1. Is it a special pattern? It's a binomial with a minus sign. Is this a difference of squares? Can you take the square root of a to the 4th? Well, because it's an even power, you can. The square root of a to the 4th is a to the 2. Because a to the 2 times a to the 2 is a to the 4th, can you take the square root of 625 and get a whole number? You can. That makes 25. So because both of these terms are perfect squares, this is called a difference of squares. The pattern has 2 parentheses. It goes a squared times a squared makes the a to the 4th, and positive 25 times negative 25 makes the negative 625. Now inspect both of these to see if they fit a pattern. The first one is a binomial, so the pattern we're looking for is called difference of squares. But it's not a difference. It has a plus sign. This other one is a difference of squares. Hopefully you recognize that you can take the square root of a squared getting a, and you can take the square root of 25 getting a 5. So our final answer begins with a squared plus 25, but the a squared minus 25 will factor into 2 sets of parentheses. A plus 5 times a minus 5. Now number 8. All the terms divide by 4. So write that down. That's called the greatest common factor. And then put a set of parentheses following it with enough space to put in a trinomial. 4 times what is 4a squared? We need the a squared. 4 times what is the 16a? We need a positive 4a. 4 times what makes 16? We need a positive 4. Now look at that trinomial. Is it a special pattern? The pattern we're looking for trinomials is called a perfect square trinomial. You have to be able to take the square root of the first thing and get a nice result. You have to be able to take the square root of the last one and get a nice result. And the middle term has to be twice the product of these. If it fails any of those tests, then it's not a perfect square trinomial. But this one is, so we're going to factor farther. 1 set of parentheses with squaring on the outside. And in here we put our a and our plus 2. Number 10. This one begins with a negative sign. If you ever have a negative leading coefficient, you start by factoring out a negative, or you might think of it as a negative 1. Either way. That leaves x squared minus 50x plus 625. Now look at that polynomial. Is it a special pattern? Well, it's a trinomial, so what we're looking for is it a perfect square trinomial? Can you take the square root of x squared? Yup, you get x. Can you take the square root of 625? Yeah, you get 25. Is the middle term twice the product of these? And it is, because x times 25 is 25x, and twice that is a 50x. So final answer begins with that negative 1, and then it has a set of parentheses squared. Fill in the x and fill in the 25. What sign do you need here? It's a minus sign because this term is a negative. Number 12. This has 4 terms. So let's try that grouping method. Make a binomial and then make another binomial. In the first binomial, look for a greatest common factor. There isn't one other than 1, nor is there in the second binomial. So grouping doesn't work if the terms are written in this order. But maybe rearranging the order would allow grouping to work. Let's try that. Let's keep the 2ax at the beginning and follow that with the positive x, then put the positive 6a, and then put the plus 3. Now let's try grouping. The first binomial has a GCF of x. X times 2a makes the 2ax, and x times positive 1 makes the positive x. In this binomial, there's a greatest common factor of 3. So write down positive 3 and then the parentheses. 3 times 2a makes the 6a, and 3 times positive 1 makes the 3. Now we were able to create 2 terms that have a 2a plus 1 in common. So our greatest common factor is 2a plus 1, and then in another set of parentheses, put the x and put the plus 3. It seemed like grouping didn't work, but if we rearranged the terms, we found out that it does work. Number 14, all the numbers will divide by 6. So let's factor out a 6. Here we need an s squared, and then 132 divided by 6 means here we need a 22, and then 726 divided by 6 tells us that here we need a 121. I was using a calculator to figure out the 22 and the 121. Now look at this trinomial. We want to see if it's a perfect square trinomial. The square root of s squared is an s, and the square root of 121 is an 11. S times 11 is 11s, and twice that is 22s. This checks out. So the final answer begins with 6, then one set of parentheses with squaring, and fill in the s plus 11. I'm using a plus sign because of that plus sign. Number 16, all of the numbers will divide by 3. That leaves x squared plus, now take a calculator and go 84 divided by 3. We find out that the middle term is 28x plus, now take a calculator and go 588 divided by 3. And the last term is 196. This is a trinomial. So the only pattern that we know about for trinomials is called a perfect square trinomial. We want to test to see if it fits that. The square root of x squared is x. The square root of 196 is 14. X times 14 is 14x, and twice that is 28x. It fits the pattern. So one set of parentheses squared, and you fill in your x and your 14 that you figured out. Number 18, there's no greatest common factor. We want to see if this fits a pattern. It is a binomial. So is it a difference of squares? Well, it is a difference. It has a minus sign, but these exponents are odd numbers, so they're not perfect squares. Is it a difference of cubes? Well, yes, it is, because these are obviously cubes. So as soon as we know it's a difference of cubes, write down the parenthesis pattern that you use to factor it. The cube root of r cubed is an r, and the cube root of s cubed is an s, and that's what goes in there. Whatever this sign is, it's used there. Then we create the trinomial from this binomial. Take the r and square it. Take that sign and switch it. Now take the product of the two things, that's rs, Now use a positive again. Take the s and square it. Here's our factored form. Number 20, there's no GCF. Is this a special pattern? Well, it is a binomial. Is it a difference of squares? Well, no, it's not a difference. Is it a sum or difference of cubes? Well, it is a sum. Let's check if these are perfect cubes. Can you take the cube root of 8x cubed? You can. It would be 2x, because 2x times 2x times 2x is 8x cubed. Can you take the cube root of 1 and get a whole number? Yes, you can. It's 1. So because they're both perfect cubes, we know it's a sum of cubes. Small set of parentheses, longer set of parentheses. Fill in that 2x, fill in that 1, and use the same sign as what that original problem had. Then create your trinomial from using those parts. Take the 2x and square it. You get 4x squared. Switch to a minus sign. Take the product of those two things. You get 2x, then a plus sign. Take the 1 and square it. You get a 1. Number 22. Is this a difference of squares or a difference of cubes? It's a difference of cubes. I'm led to that conclusion by noticing the cube. But it's only a difference of cubes if you can take the cube root of both of those things. So the cube root of 125y cubed is 5y, and the cube root of 1 is a 1. So a small set of parentheses and a large set of parentheses. We already figured out the 5y and the 1. What sign goes here? It's a minus sign because it fits that sign. Then create your trinomial. 5y squared makes 25y squared. Switch to a plus sign. Take the product of the two things, that's 5y. Plus sign again, and square the 1. Number 24 has 4 terms, so we want to try grouping. So let's group these together and group these together. In the first binomial, both of them divide by a, leaving a plus b. In the second binomial, they both divide by -2. So write down -2, and then in parentheses, we have a plus b. Notice that both of these have an a plus b in common. So the final answer is a plus b. And then in another set of parentheses, take the a and take the -2. The review assignment goes back to page 132, where we were practicing making prime factorizations, taking numbers and figuring out the product of prime numbers that equal the number. The systematic technique was to try to divide by prime numbers. Try dividing by 2, but it won't because it's not even. Now try dividing by 3, but on a calculator you'll find out that that would make a decimal. The next prime number is 5, but it won't divide by 5 because it doesn't end in 0, 5. The next prime number is 7. Take a calculator and go 343 divide by 7. You'll find out you get 49. So we can write this as 7 times 49. One more step. Rewrite the 49 as 7 times 7. So we see that our prime factorization is 7 to the 3rd power. Number 4. Take 156 and divide it by 2 on a calculator, and you'll get 78. So you know you can write this as 2 times 78. Well, 78 is an even number, so it divides by 2. So now we have 2 times 39, where we're using 2 times 39 to replace 78. Does 39 divide by any prime numbers? It divides by 3. So now we have 2 times 2 times 3 times 13. And 13 is a prime number, so we're done. Our answer is 2 squared times 3 times 13. Number 14, we're going to find the greatest common factor and the least common multiple. To help us do that, we can factor out this expression or expand out this expression. This is equal to -1 times 3 times A times B times B times B. This one over here is equal to 2 times 2 times 3 times A times B times B times B times B. Make sure you agree that the number 12 prime factors into 2 times 2 times 3. Now let's look for the greatest common factor. We want to find the common factors. What appears in both of them? You can ignore the -1 because greatest common factors are always positive numbers. Do they both have a 3? Yes, they do. So for our greatest common factor, let's use a 3. Do they both have an A? Yes, they do. Let's put an A in our greatest common factor. Do they both have another A? Nope, this one doesn't. But they both have 3 B's. So in our greatest common factor, let's put B to the 3rd power. Both of these original expressions will divide by 3AB cubed. Now let's find the least common multiple. Least common multiples are always positive, so we can ignore this -1. From the first number, we're going to take the 3. And we're going to take a pair of A's. And we're going to take 3 B's. Now go to the other number and write down any factors we haven't yet used. We haven't used these 2 2's. We already used the 3. We already used an A. But we only had 3 B's so far, and this has a 4th one. So add that to the list. Now multiply this all together. 3 times 2 times 2 is 12. A times A is A squared. And the 4 B's are B to the 4th power. Here's our least common multiple. On page 129, we're asked to simplify. We're going to multiply the binomials together using FOIL. S times S is S squared. Our outer product is -4ST. The inner product is -3ST. And the last product is negative times negative, which is positive, 3 times 4, which is 12, and t times t, which is t squared. Then combine those like terms together. We get -7ST as our middle term. Number 22, let's use FOIL. A times A is A squared. A times 2B is a positive 2AB. -6B times A is a -6AB. And -6B times 2B is -12B squared. Then combine those like terms together. In the middle, we get -4AB. Number 26 is also a binomial times a binomial, so we're going to use FOIL. But we can make it faster if we recognize the special case. This is -3y and this is +3y. So when we do FOIL, the outer and inner products will just end up canceling each other out, and we'll be left with a binomial. So if we know that ahead of time, we can go 1 times 1 makes 1, and -3y times +3y makes -9y squared. Notice that our answer is a difference of squares, and we've recently learned how to factor that answer. When you factor it, it creates that. So there's certainly a connection between multiplying things out with FOIL and factoring things. They are opposites of each other.